Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos that give a basic introduction to vectors. And in particular in this video I'm going to talk about lines in 3 dimensions, or R cubed. We're going to talk about the parametric vector form of a line, the Cartesian form of a line, and the relationship between the two. So let me share my screen with you and we'll get down to business. Okay, now here's a slide that I'm going to talk and share with you today. But before we do that, let me just go back to the previous slide from the previous video. Now, the parametric vector form of a line, say L, to formulate a parametric vector form, you just need a point on the line and the position vector associated with that point, and a vector parallel to the line. And using the triangle rule of addition, you can just stretch this vector v to any point on the line to give you this vector of interest. And in the previous video, I talked about the 2-dimensional case and I gave some examples. So this raises the question, what about the 3-dimensional case and higher dimensional cases? Well, the parametric vector form works in n dimensions, 2, 3, 4, 5, etc., all the way up to n. So in this video, I'm just going to talk about the 3-dimensional case. All right, so suppose I have a line L, and that line is parallel to this vector here, which I've written as a column. And suppose the line L passes through the point A, where A might have coordinates, say, A1, A2, A3, and A has position vector denoted by this bold-faced lower case letter, A1, A2, A3, written as a column. And the parametric vector form for L is the following. Now, this boldface X is, at least in 3 dimensions, is just going to be this column vector X, Y, and Z. Now, some people write this as X1, X2, X3, so you can easily go up to n dimensions. Well, I'm not going to do that. Now, we can also form an equivalent Cartesian form for the line in the following way. The Cartesian form for the line L that's parallel to the vector V and passes through the point big A with position vector little a is just this here. So A1, A2, A3 are the components, if you like, of the point A, and V1, V2, V3 are the sort of components of the vector V. Okay, now I have put the equals lambda in brackets here. Strictly speaking, you don't have to do that, but I just like doing it because first of all, it reminds you that you can get back to the parametric form pretty easily. So where does this come from? Well, that's what I'm going to discuss. In other videos, I'll follow up with some examples, and I'll do some examples in this presentation as well. But where does this come from? Okay. So let's start with the parametric vector form. And remember, as I said in the previous video, there's an infinite number of ways to parameterize a line. And let's see if we can get down to the Cartesian form, which is that there's only one for the Cartesian form. It's a little bit more definite. Okay, so from x equals a plus lambda v, if I write these out as columns, then we get the following. And essentially, each component has to equal the corresponding component on the left and right hand side. So I can form 3 equations there. Okay, we obtain the following. So x is going to be a1 plus lambda v1. Y is going to be a2 plus lambda v2. And z is going to be a3 plus lambda v3. Okay, so what we want to do now is isolate the lambdas. Okay, so I take the a1 over there and divide by v1. Okay, so I've isolated the lambdas. We can make these all equal to each other. Okay, and if I wanted to, I can put this lambda in over here. All right, so there we have it, the Cartesian form of a line in three-dimensional space. Okay, now to go from here to here, of course, well, you would start with something like that. You would let lambda equals any of these things, which are jointly equal to each other, and then you would just reverse the steps as we that we used here. Okay. All right. Well, some of you may be looking at this expression and go, well, what happens if, say, v1 0? Can't divide by 0, so what do we do? Well, I just wanted to briefly discuss that. Okay. All right. So if, say, v1 equals 0, then we'd write the following. Okay, x equals a1 together with these two equations here. Okay, and here is v2 and v3 are non-zero. All right, so this then would be the Cartesian form of the line that passes through the points a1, a2, a3 and parallel to the vector v, which has a 0 first component, v2. Okay, and if say v2 was 0, then you would have y equals a2 or something like that. All right, with the other two equations equal. Okay, so why would you want to have two forms of expressing one line? Well, sometimes this form is easier to work with, and sometimes this form is easier to work with. And in the examples that I'm going to show you in forthcoming videos, it'll be clear that sometimes this is easier to work with, and other times this is easier to work with. So that's a very brief discussion about vectors and using vectors and parameterizations to describe lines in three-dimensional space. So please join me for my next presentation where I'll step you through some examples involving lines, parametric vector equations for them, and also Cartesian equations for them. Hope you can join me for those presentations.